So we have been talking a whole lot about electrons, where electrons are found, how do we organize them, and the kind of thing to wrap up this whole electron discussion that we're going to look at is a special class of electrons that we call valence electrons. We've spent all this time talking about like where to put them and electron configurations, and now I'm going to kind of like, burst the bubble a little bit and say, yeah, we only really care about a certain category because those are the ones that actually do stuff. But we break up electrons into two categories. There's valence electrons and there's core electrons. Valence electrons are those that are in the highest energy level or highest N value. So again, just to review, we can always determine N by the row, 1, 2, 3, 4, 5, and so on. And the core electrons are pretty much everything inside. These are pretty much inert, meaning they don't do much. And it's valence electrons that get to do all the fun stuff. Those are the ones that are involved in chemical reactions. Those are the ones that move around. Those are the ones that um, either get taken away or added to. Those are the ones that will make chemical bonds involved in bonding. And so that's what those are the ones that we like to focus on. So how do we quickly determine the number of valence electrons? Now I'm going to focus just on what are known as the main group elements. That's these first two columns, or the S block, and then these last six columns, or the P block, minus helium. Helium's kind of an S block element. I'll tell you why they put helium there in a little bit, but yeah, it's kind of weird. Um, and so if we look at let's just take lithium, for example. What is its outermost energy level? Well, that would be 2s1. And sodium is 3s1, potassium 4s1. And so all of those elements in the first column have one valence electron. What about like beryllium, number 4 here? Well, it ends in 2s2. Magnesium ends in 3s2, and so on and so forth. So all of those elements have two valence electrons. Okay, let's shoot over to boron. Boron, its um, outermost configuration, 2s2, 2p1. That's the highest energy level. We don't care about the 1s2. That's not a valence electron. We're just focusing on those that have the highest energy level. So all of these elements have three valence electrons. And then these would have four and five and six and seven, finally eight for all of these elements except helium. Helium again is a weird guy. Helium can only have two valence electrons because it's so small. But all these other ones here, all of those have eight valence electrons. And this is going to kind of transition us into our discussion of what we call periodic trends, where we're going to be noticing the way that the periodic table is organized is not random. It's organized to show that there are actually quite a few number of reoccurring and predictive trends as well. And when it comes to like why atoms in the same column act very similar, so elements in the same column behave similarly because they have the same number of valence electrons. So let's transition into this discussion of periodic trends. So just a quick introduction to this. The periodic table and what we're going to be discussing, the periodic trends, is based off of something known as the periodic law. Periodic law says that when organizing elements by mass, certain properties reoccur periodically. So the scientist Dmitry Mendeleev is kind of known as the father of the modern periodic table. This was way back when in the 1800s. Not all elements had been discovered yet. They didn't even have quantum mechanics yet. But what he noticed was that if he took the elements and kind of maybe laid them out in cards or, however he did it, he noticed that certain trends would occur periodically. And so, for example, and what would happen is that you would notice some holes in his columns or in his rows. So, like, for example, he knew like carbon existed and silicon existed, but then there was this hole between that and tin. And that element hadn't been discovered yet, but he knew that there must be an element there because um, there's like way too big of a gap between the mass of silicon and tin. And so he basically just, well, there's supposed to be an element there, and I think I'm going to predict what the properties were. So that's what this little table here is. And I'm not expecting you to memorize anything on this. I'm just using this as an example. So he knew that this element was below silicon. He called it Eka silicon, which is just basically, his prediction. So he predicted these things. And he basically said, well, it should have all of these properties. Once it gets discovered, it should have somewhere around those. And if you look at it, he was pretty darn close to what those properties actually were just by noting what column it was in and what the properties of silicon were right before it and tin right after it. And he was actually able to do that for quite a bit of the periodic table. And those elements got filled in as they got discovered. And again, I want to highlight um, that he was able to organize these things into trends. And later, once quantum mechanics was developed, quantum mechanics actually helped explain why those trends occurred. So let's get to our first trend, and that's the common charges. So again, I'm going to focus just on the main group elements. Transition metals are kind of weird, but I'm just going to focus on the main group elements. But there is a noticeable trend in when these elements become ions, they tend to form the same charge every single time. So I'll go over the trend and then we'll kind of talk about why. So all of the elements in the first column will form, when they form an ion, it's going to be plus one. Hydrogen is kind of an exception. We will see hydrogen as plus one or minus one. But everything else from here on down, those are all plus one. All of these elements will be plus two. All of these elements will be plus three. And I'm going to kind of skip over the fourth column here and just go right to nitrogen. But all these elements will form ions of minus three, and then minus two, and then minus one. And then that final column tend not to react very much. That's why they're all together. Just a little side note, and I'll talk about this a little bit later. They call these guys the noble gases because they're so noble. They don't like to hang out with other elements. They don't like to react. And so you don't really, see them with a charge very often. There might be some weird exceptions here or there. Um, and then just to kind of go back to this fourth column, it could go either way. Sometimes you'll see it with plus four, or sometimes you'll see it minus four. But the trend here you can see is that all those elements in a particular column will have a very similar, or I should say, will have the same exact charge when they form ions. Now, what I want you to do is I want you to look at nitrogen, oxygen, fluorine, and then sodium, magnesium, aluminum. So when those are ions, we have N minus 3, O2 minus, F minus 1, and then sodium plus 1, magnesium plus 2, and aluminum plus 3. There's one thing that is common to all of them. These all have the same electron configuration as neon. And you'll notice that the charge I gave them were the common charge for their column. All the elements in the nitrogen column like to be minus 3 when they're an ion. All the elements in the sodium column like to be plus 1 when they are an ion. And the reason for that is that most of these main group elements want to be like a noble gas. And what is a noble gas? Why are noble gases special? They have a filled valence shell. If you look at the electron configuration for neon, so 1s2, 2s2, 2p6, here's the valence shell. And I encourage you, take some time, do the electron configuration for all of these. And long story short, they're all going to have this same configuration. They're not equal in identity. Remember, it's not the number of electrons that determines the identity. It's the number of protons. So N3 minus, okay, when nitrogen is an ion, it's still nitrogen. It just kind of looks a little bit like the noble gas neon because it has the same electron configuration. Now, the next trend we're going to look at deals with the size of the elements. And we're going to look at this from a lot of different aspects. When we go through a periodic trend, there are two main important things that you should know. You need to know what the trend is, and you need to know why that trend exists. What is it that governs that trend? Now, the first important thing to note is that different elements are different sizes. So the general trend, this is the what of atomic radius, is that as you go down the periodic table, size increases. And the general trend is that as you go from left to right, size decreases. Now let's talk about why size increases going from top to bottom. So I want you to kind of think about that a little bit. So why would size increase going from top to bottom? Well, as you go from the first row to the second row to the third row and so forth, N is increasing. The energy levels are increasing. Think about adding another floor to your electron hotel. So lithium has 2 floors, sodium has 3, potassium has 4, and so on and so forth. So you're literally increasing the radius by adding more quote unquote electron floors or energy levels to the atom. Now that doesn't explain why, as you go across a row from left to right, size goes down because they're all on the same floor. So why would the size go down? This has to be explained with something known as effective nuclear charge, what we say ZF. Effective nuclear charge. The simple way to kind of put it is how much do the electrons feel the nucleus? The bigger this number is, the more the electrons feel the nucleus and the smaller the atom is going to be. So the way you can easily calculate this is you have Z, which is number of protons, we learned that last unit, minus S, and this is the number of shielding electrons. Okay, let's do this for boron. Boron has 5 protons. So if I use the Bohr model just to kind of illustrate this, there's the nucleus, and then I have n equals 1 right here, and then n equals 2. So I'm going to put my 2 electrons there, and n equals 1. That's like the 1s2. And then so 1s2, 2s2, 2p1. I have 3 electrons and n equals 2. So I'm going to put those there. So the effective nuclear charge has 5 protons. And the number of shielding electrons are how many electrons are between, say, this level and to the nucleus. So there's 2 between n equals 2 and the nucleus. So the effective nuclear charge is +3. Now, let's compare this to something like fluorine. Notice it's kind of maybe a little hard to see. I'm going to zoom in there. Fluorine, a little bit smaller than boron there. So why would the size go down? Well, fluorine has 9 protons in its nucleus, and its electron configuration looks like this. So again, we'll use the Bohr model. So we'll put our nucleus there. N equals 1 with 2 electrons, and then n equals 2 with all 7 of those. Just kind of put them around there. And when we calculate the effective nuclear charge, there's 9 protons. Again, only 2 shielding protons. So that effective charge is +7. What that means is that these electrons on the outside feel the pull of the nucleus a whole lot more than these electrons in boron. And so it's basically, like I said, just to summarize that, those electrons on the outside feel the pull of 7 protons versus in boron, they only feel the pull of 3 electrons. So it's like sort of like tug of war, where the electrons in fluorine on the valence shell are being pulled a lot closer to the nucleus. And so that radius is going to decrease. And then just to kind of compare the two trends, going up or down has a larger effect on radius than going left to right. Now, let's take a look at ionic size. So if a neutral element gains or loses electrons, its size will change. So ions have different sizes than its neutral atom. All right, again, let's use lithium as an example. So lithium, when it becomes an ion, is almost always lithium plus one. So let's compare, again, use the Bohr model. There's our nucleus. There's n equals 1, 2 electrons. There's n equals 2 with its 1 electron. Now, again, this highlights what I said earlier about valence electrons. They get to do all the fun stuff. When lithium loses that electron, it always comes from the valence shell. So it's going to go away. Okay, kind of think of it like, okay, I'm lopping off an entire floor of a hotel. So what happens to this electron hotel? Well, now there's only n equals 1. So the size goes down. If you look at this little diagram to the right, this picture to the right, look here at lithium. The gray sphere is neutral lithium. The green sphere is when lithium becomes an ion. Notice how much its radius decreases. Now, what about if something gains an electron? Well, let's use oxygen as an example. Oxygen has 8 protons. Oxygen, when it becomes an ion, is almost always -2. Still has 8 protons. So we'll use the Bohr model again. There's n equals 1 with 2 electrons in it. And I'll write out the electron configuration here. 2s2, 2p4 for oxygen. So when n equals 2, there will be 6 electrons in that valence shell. 1, 2, 3, 4, 5, 6. Now, again, oxygen wants to be like a noble gas. So if it were to gain electrons, it would gain 2 more so that it would have a full valence shell. So if we draw the Bohr model for oxygen -2, it now has 8 valence electrons in n equals 2. 3, 4, 5, 6, 7, 8. Now, when something gains electrons, the trend is the size is going to increase. Why is that? Well, let's just think about what an electron is and what happens when we're adding more. Electrons are negatively charged, and if you put more like charged things in the same environment, they're going to repel each other. So the radius increases to allow the electrons to spread out. And again, you can see this here on the table. Neutral oxygen is there in gray. Oxygen -2 is there in purple. So the general trend, cations tend to decrease in size. Anions, when they gain electrons, or as they gain electrons, become bigger in size. Probably be a good thing to write down. Cations lose electrons and therefore become bigger. I'm sorry, smaller. Anions gain electrons and therefore become larger. All right, and the final thing I want to talk about with size is dealing with elements that are isoelectronic. Now, if you just kind of break down that name, well, we haven't heard it before, but iso meaning same, electronic referring to electrons. Isoelectronic ions are ions that have the same number of electrons or same electron configuration. Now, even though they have the same number of electrons, same electron configuration, their size is not going to be the same. Let's compare sulfur -2 with chlorine -1, potassium +1, and calcium +2. These are all isoelectronic to argon. Sulfur has 16 protons, chlorine has 17 protons, 19 protons, 20 protons. Now, since calcium has the most protons, it will have the higher effective nuclear charge because all the numbers of electrons are the same. But there will be more of a pool from the nucleus of calcium +2 on those outer electrons, so it will shrink the radius. So of all four of those ions, calcium will be the smallest. On the flip side of that, since sulfur -2 has the least number of protons, which means lower effective nuclear charge, or I should say the lowest of this group, it will have the largest size. All right, in our next lecture, we're going to kind of get away from size and look at some other important trends of the periodic table.